Hello, everyone. So we are going to get started here. I did want to give a couple extra minutes for those to log on as we are switching over to our new format with Teams webinar in here. So bear with us as we make this transition in here. So we'll go ahead and get started, and then those that will still join will be able to get this access. So I just wanted to thank you for joining us first and foremost, and also appreciate all of your patience as we transitioned, as I said, from the standard Zoom's meeting format into the Teams webinar format. So we appreciate your patience, and I especially appreciate your tolerance for the many emails that we've sent as we transition. So we appreciate it and thank you. And so today's webinar is going to be is on the CICPs, and this is, as we've done before, will be recorded, and the link for the recording as well as the PDF of the presentation will be sent to all of those in attendance today, so that you have access to it. And if those who were not able to join through whatever technical issues that they might have had as we transition, they will also get the recording as well. With that, also, if there's any questions that you might have, feel free to use the chat box to enter those questions, and I will address them at the end. So we'll go ahead and get started. So we are talking about the CICPs, and we'll go ahead and start it on here so that I can. So CICPs, as we've talked about in previous webinars, they are part of the inorganic grouping of pigments, and they are synthetic in nature. And they do have a structure towards them. So they have a unique category in this subsegment of inorganic pigments. Just to drill down a little deeper in the inorganic side of the pigment house, of those structured synthetic inorganic pigments, of which the CICPs fall in, there are two main classes, the spinels and the rutiles, and you might recognize a number of these chemistries in your usage today. But it gives a little more in-depth into how some of these might fit into the different categories of colorants. CICPs, they are a mixed metal oxide, which is an inorganic pigment that contains more than one metal ion type in the crystal structure itself. As a comparison, iron oxide is a metal oxide. However, it only has one metal in it, obviously just the iron in here. So CICPs have two or more in its structure. So CICP stands for complex inorganic colored pigment. It's often used interchangeably with mixed metal oxide, but the acronym CICP designates that this pigment is colored, whereas the mixed metal oxide may not be colored in nature. So these are synthetic crystalline metal oxides that do have structures that are identical to some naturally occurring minerals. However, because they are synthetic, this results in the ability to control all of the physical properties of that colorant. They are complex. As I stated, there are two or more metals which provide a wide range of colors. As far as properties is concerned, They do have outstanding color stability. They are resistant to chemicals and solvents. They don't bleed or migrate, and they have a very high heat stability, typically hundreds of degrees above organic pigments in a similar color space. And with all of these properties, they are truly a high-performance pigment. The one main negative, if you can really call it a negative, would be its strength. And typically it's a negative because it's compared to an organic pigment in a similar color space with regards to strength. However, all of the other properties do make it a very attractive colorant to use in various applications. So I would be remiss if I did not use the periodic table when we're talking about inorganic pigments. So with respect to the CICPs, the ones I've highlighted here in red, these metals are responsible for the primary color of the colorant. And the ones that I've highlighted in blue are primarily responsible for balancing out the charge of that crystal structure, as well as to modify the color hue in the crystal structure. And we'll revert back to these items as we move through the presentation and discuss specific color indexes. So the CICP structure is always determined by the oxygen-metal ratio in that structure. Primarily, there are two structures that dominate the class. The first is the rutile, and the second is the spinel. The third is hematite, which is much less common, but it is a third category. This chart here is a very has a lot of information in it of some general common CICPs that are being used. Provides obviously the color index name, the actual chemistry of the structure, its name, and the structure category. Again, the spinels, rutiles, and hermatites. Its color, and then the name of the colorant also indicates some information about what kind of substructure this item or product is classed under. So you'll see I've highlighted here chromite, titanate, aluminate, and ferrite. So that'll give you a clue as to the substructure that these fall into. So the first structure is the rutile. These colorants have an oxygen to metal ratio of 2. They are octahedrally spaced by the 6 oxygens depicted in the caricature here in the slide. Rutile is one of the crystalline phases of titanium dioxide. It is the most dense. And the CICPs in this family do contain a very large fraction of titanium dioxide, typically somewhere between 70 to 90% by pigment weight. The rutile CICPs have many physical properties that are common with TiO2 because of the large amount of weight ratio of the TiO2. And the colors in this class range from light yellow to dark brown. However, they do not possess the same photodegradation properties that TiO2 does. So that's one positive part of the rutile CICPs versus a straight TiO2. The second grouping is the spinels. Here, the oxygen to metal ratio is 1.3. These are named for the mineral spinel, magnesium aluminum oxide. And these crystal structures contain metal ions that are in both the divalent stage as well as the trivalent oxidation state. And there are 2 different coordination environments for these metal ions. The trivalent are octahedrally spaced while the divalent ions are tetrahedrally spaced by the oxygen. And the third category, the smaller category, is the hematite. The oxygen to metal ratio here is 1.5. The hematite is based off of iron oxide, where a similar in another group, another name in this category is the corundum, and it is based on the aluminum oxide. These, in this crystal structure, the metal ions are trivalent and octahedrally coordinated. And then, as I mentioned in an earlier chart, there are three groups or substructures of the CICPs. The first one is the titanates. These, as the name implies, are TiO2 based, and these are the largest volume of CICPs that are in production today. These rutile grades, the rutile grades of titanates are the largest volume in that subgrouping. And these range, as I mentioned, from light yellow to brown. The spinel titanates are smaller in volume, and these range in color from green to brown. The second group is the aluminates, and as the name also implies, the aluminum oxide is the base for these. They are all in the spinel crystal structure category. And they almost always use cobalt oxide as the coloring oxide. And the color ranges from a blue to a teal type of a color. And the third category contains the chromites and the ferrites. And they are chrome and or iron oxide based in these categories. So as far as the rutile, I've just listed here some of the more common rutile CICPs, just to give you a feel for the color index, the actual color, the metals that are used in this class, in this structure, and then the class, of course, is rutile. And in this case, all of these are titanates as far as the subclass is concerned. In today's webinar, we'll take a closer look at pigment yellow 53, pigment brown 24, and pigment yellow 164. Spinels have a larger variety of colorants in this category, with a larger variety of color as well. So here again, you can see the color index, the color, the metals that are associated with this particular one, and then of course the subclass. And this subclass contains all three of the subclasses that we just described. In today's webinar, we'll take a look at the pigment green 50, pigment blue 28, pigment blue 36, pigment green 26, pigment yellow 119, which is also under the category of pigment brown 31, and lastly, pigment black 28. And the third category in the hematite is the pigment green 17, which is also known as pigment brown 29. As far as the usage of CICPs, they are primarily being used in the coatings and plastics areas. In coatings, they have their properties of high opacity, high durability, and heat management make them very good tools for architectural type of coatings, as well as good durability coatings as well. And similarly in plastics for the same types of reasons, as well as the heat stability aspect of it being very high. So as we go through the individual color indexes, these, as I mentioned, these CICPs tend to have very, very similar physical properties. So I won't repeat myself so much, and I'll really just highlight some of the key different uniquenesses for each of the color indexes. so that you don't hear my repetition of the same type of information. So we'll start in the rutile category, and we'll start with pigment yellow 53. With this color index, the nickel is the primary coloring metal ion that gives it its light yellow color and shade. It is a very good dispersible colorant with very good near IR reflectance. This particular color index is the second highest volume of CICP that is used. And when it was important in the US to do so, this color index was a very useful product for replacing chrome yellows when in combination with other organic pigments. But for the most part, I think most of the conversion from chrome yellows has already been completed. For Sudarshan, we plan to introduce 2 products in this space. And those are expected in November for introduction. Moving on to the next rutile is pigment brown 24. Here, the coloring metal ion is the chromium, and that results in a clean buff shade in color. This happens to be the very highest volume CICP in use today. A wide variety of uses, both in polymer, in plastics, and in coatings areas. This one was also very useful for chrome yellow replacements. For Sudarshan, we will have one product, or our first product to be introduced again in November. This will be part of our Sudatherm range of products. It'll be buff yellow 6431. And then the last one in the rutile class is the pigment yellow 164. Here, the coloring metal ion is the manganese, and this results in a dark brown shade in color. This has very good dispersion, high near IR reflectance, and is very useful in many applications. We've recently introduced this product, the Sudatherm Brown 6411, just this month, and so is one of our first in our range of CICPs. So just to go back to the concept of the choice of metal ion for the primary color, I just wanted to bring these 3 together because the structures are very similar, as you can see by their formulation. However, the color, I wanted to take note how the color changes going from the nickel with the pigment yellow 53 through with the chromium in the pigment brown 24, all the way through to the manganese with the pigment yellow 164, giving that brown color. So it gives another aspect as to the importance of that primary coloring metal ion. And now we switch over to the spinels, and here we start with the pigment yellow 119, and here the coloring iron is the iron. And that results in a reddish buff shade, more towards the yellow side than the red side, like the pigment brown 24 was. Here we start to have a little bit more moderate IR reflectance. However, this colorant tends to find some good uses when mixed and when combined with other organics and inorganic pigments to reach more natural colors like greens and bright reds or chocolate browns to also help with a good cost position. So as far as Sudarshan is concerned, we will introduce our Sudatherm Buff Yellow 6416, and that will come in December timeframe. And moving on to Black 28, here we have 2 metal ions, the copper and the chromium, which provide the color, and this results in a bluish black shade for color. This has very good IR reflectance in there, so it does provide a lot of uses for coatings in terms of cool coatings for heat management, as well as in plastics to help with some recyclability as well. And we've recently introduced this color index into our line. It is Sudatherm Black 6461. And next up is the Pigment Blue 28 here. The cobalt is the coloring metal, and this results in a red shade blue color, and is this one does have a little bit more moderate weatherability than some of the other CICPs in the line in the chemistries. And our product, Sudatherm Blue 6421, that will be making its introduction again in November. The other blue, Pigment Blue 36, here we've transitioned from one colorant to two colorants, two metal ions to provide color. Here we are also using the cobalt and the chromium to provide a green shade blue in color. And this one also has a very unique color with that teal green color, moderate IR reflectance. And in early next year, we will introduce our Sudatherm Blue 6426 into our portfolio of CICPs. Moving on to the green space, Pigment Green 50. Here again, the cobalt is the coloring metal ion. This provides a bright green shade with very good dispersion characteristics and excellent dimensional stability. Definitely has a wide variety of uses. It has a very interesting color, so that the opacity that comes with it provides some very useful properties in the various applications. This product will be launched at the end of this month, and it will be our Sudatherm Cobalt Green 6451. The other green, Pigment Green 26. Here again, we bring in both the cobalt and chromium for the coloring nature of it. This results in a dark bluish green in color. And this one, as soon as I say it, provides some excellent camouflage properties. It'll hit you right away that this kind of has this, a very good color associated with, that army green, the camouflage green that is very used in there. So it's with its opacity to visible light, it helps with those camouflage properties. And this product, the Pigment Green 26, will be launched early next year into our Sudatherm product lineup. And again, going back to those coloring ions, metal ions, here we're comparing the Green 50 to the Green 26, where not necessarily a metal ion. Here we're replacing some of the secondary titanium with chromium to get that color to move from the yellow side to the blue side in this green space. And similarly in the blue space, going from Pigment Blue 28, Pigment Blue 26, we are substituting some of the secondary aluminum with chromium to move it from the red shade to the green shade. So again, it's always interesting to compare the chemistries and to see how this switching out some of the the ions in there to move the color positioning. So as far as the synthesis is concerned with respect to CICPs, these are made by calcination, which is a process of strong heating in the presence of air. And this is, we take up blends of metal oxides and or metal oxide precursors and mix them together and send it through a kiln for that calcination process. There's two zones that in that process that create these CICPs. At the lower temperature, the materials begin to decompose to the metal oxides, and at the higher temperatures, at the end of the kiln, the oxides become reactive in order to create the final crystalline structure. At these higher temperatures, as I mentioned, the solids then begin to rearrange to form that final stable crystal structure. And as I mentioned earlier in the presentation, this structure is always going to be determined by the metals present, and which is then the formulation, if you will, the oxygen to metal ratio. Again, that goes into the part of the formulation, as well as that kiln temperature near the end where the final conversion is made. And that is more process oriented. And then once it's calcined and created, the product is then milled to the appropriate particle size. It is washed and then blended into the final lot. And so as we move through the development of these products, as well as our manufacturing, it's always important to know and understand as much as we can about the process and the formulation so that we can produce quality product consistently. But it also helps us to investigate other places that we can take these products for potentially new product developments. And so I wanted to share with you a couple of examples of this knowledge base that we develop along the way as we develop these products. And so I brought two examples today for this webinar. The first is pigment brown 24. So as I mentioned, there's formulation and there's process when putting together these color index. So the chemistry is always going to be the same, the final end chemistry, but how you get there can impact the color. So in this particular case, we're taking a look at the color impact by compositions, and this color is evaluated in a high density polyethylene. So you can kind of see where we are placing our initial product in the Sudatherm product portfolio. However, the color in the red space can alter about 2.5 units. In the yellow space, about 1.5 units, depending on how that formulation and process is manipulated. So this allows us to potentially introduce other products and know how to get to that spaces. The second example that I've included in this webinar is pigment blue 28. And in this slide, I also have put in a reference point for pigment blue 15-1 and the organic that shares a very similar color space to the pigment blue 28 in here. So you can get a better feel for how these two color index products fall with respect to each other. So the next slide, I'm going to remove the pigment blue 15-1 so we can get a better feel for the impact of formulation and process on the color of pigment blue 28. So here you can definitely see there's a lot more options with respect to the pigment blue 28. In the red space, we have 11 units of space that we can cover, and in the blue space we have 14 units of space that we can cover. So you can see where our initial product is going to be, as well as some options for other products to be introduced in the future. We've are nearing the end of the webinar, and I just wanted to bring back our brands. And again, our CICPs are under the brand name of Sudatherm, and they are our newest addition to our overall colorant portfolio. Because we do have a wide variety of types of colorants to offer into all of the applications that are out there. So we are really thrilled to be able to introduce this line of colorants to you today. And so with that, I mentioned that our first two introductions into the Sudatherm line is our Pigment Yellow 164. This is just a quick snapshot of our TDS, as well as our Pigment Black 28. These are our first two introductions in the space, and we look forward to bringing you Pigment Green 50 at the end of this month, as well as Brown 24 and Yellow 53 in November. And the remaining CICPs in the line will continue to come as we bring them online. So at this point, I'd like to mention that we are going to take a break for a couple of months. We have obviously a number of holidays coming up, and everybody's getting set up to set up their end of the year activities, as well as planning for the new year. So we are going to start up the series again in February, and we are going to review solvent dyes. And then in March, we will move over to a application-specific webinar where we will take a look at pigments for inks. However, if there is something, we are always interested in hearing your feedback. So if there's something of interest that you would like us to look into, bringing to you, please just drop me a line, and we'll look towards trying to work that into the schedule for the upcoming year in this series. So we are always eager and welcoming in your feedback and in interest in this webinar series. So I am just one part of our North American team here. So we are all here to support you and help you with any questions or needs that you may have. So feel free to reach out to any one of us, and we can help in any way that we can for your needs. And at this point, I'd like to open it up to any questions that you may have, and I will address them now. And I do see a couple that have come through. The first one is, are any of these mixed metal oxides more readily susceptible to photocatalysis, and how does it affect color stability? So the good thing is these do have a very good weatherability, especially the titanates, where the TiO2 has a large metal or a large percentage in the formulation. However, it doesn't carry that photodegradation aspect that the TiO2 does. So this is a good place to, if you have, for example, a organic pigment that is susceptible to TiO2, and off the top of my head, the first one that comes to mind is maybe a Pigment Yellow 139 is particularly susceptible to TiO2. Maybe substituting out a Yellow 53 in terms of some of the TiO2 would help in that scenario. The next question was, will the pigments still sustain color at longer than 5 minutes? The typical test for heat stability is 5 minutes. However, with these being developed at very high temperatures, they will be able to withstand these longer temperatures and time frames. And the next question is, could you elaborate again in the slide where you showed the periodic table and the association to the pigments? My connection went down. Oh, okay. And all right, I will actually go back and pull that up. Oh boy. Oh, there we are. Okay, so here's the slide that you're referring to, and what I mentioned here was that those metal ions that are highlighted in yellow, those are the ions that are responsible for the primary color of the colorant, and those that are in blue, they are secondary in terms of color because they modify the color hue. But they are primarily there to balance out the charge in that crystal structure. All right, the next question was, do the CICP have any regulatory restrictions? Those will be primarily, in general, the answer is no. However, they will have to be assessed color index by color index, but a good portion of them don't have any specific regulatory restrictions, but again, we would have to take a look at those specifically. All right, if there are no more questions, I don't see any here in the chat box. If there's any last minute questions, we can address them now, or if you've come up with one later, feel free to let me know, and I will be happy to help. Again, I wanted to thank everybody for joining this webinar, and again, I really wanted to say thank you to all of those for your patience and your understanding as we moved over to the Teams webinar format, and I hope everything was pretty streamlined for you in terms of the connections and registration process. So again, thank you. And we look forward to seeing you in the new year with our series as we start up again in February. And as I mentioned, if there are any interests that you might have, please feel free to reach out to me and let me know what you might like to see in the future, and I'll try to dial that in. So with that, I'd like to end the webinar and thank you again for joining me. Take care and have a great rest of your day.